Hi, in this video we will show you some experiments about fluids, as the Newtonian and non-Newtonian fluids, and explain the properties or concepts that are related to them. As we know, a fluid is something that has the ability to flow, and the viscosity is a measure that determines the resistance of a fluid. The viscosity is not the same as the density. So, what's a Newtonian and non-Newtonian fluid? A Newtonian fluid is a fluid in which its viscosity stays constant, like water or oil. The only factor that affects their viscosity is the temperature, and these kind of fluids flow easily in movement. On the other hand, a non-Newtonian fluid has a variable viscosity. This means that will have more resistance to the movement, like the honey, and only be affected because of the force. Well, now we're going to make an experiment of Newtonian and non-Newtonian fluids. The materials we'll need is cornstarch, a bowl, and 1.5 cups of water, okay? First of all is that we are going to add to the bowl just 1 cup of water. So let's do it. It's like there, okay? 1 cup. Then we're going to add all the cornstarch to the water. Don't use more than 1 cup and a half because then the mix is going to be so liquid and it won't work, okay? So let's add this. Okay. And we're going to clean it. Now it's the fun part that we'll have to mix everything, okay? So let's mix. At the beginning, when you mix, it's going to be so like strong. Look at this. Oh my God. So be patient, okay? You can use another bowl to mix and then pour it in a new one, but I don't want to use a lot of dishes, so let's do it in one, okay? Let's just try to mix this. Well, I'm back. So, okay, now that, sorry for the disaster, but now our mixed is ready, okay? Look at this. You move it and it's like any other liquid, okay? And look at this. You are going to put your finger and your finger is going to enter easily, okay? Look, like this, okay? But now, if you apply some force to this mixed, then it's going to be solid for a moment. Look at it. I'm going to like punch it with my fingers like this. And look, I'm going to put it like that. My fingers aren't in the mix, okay? They don't sink into this mixed. Look. But if I do it like with, I don't know how to say it, but slowly, with softness, my finger is going to enter, okay? But if I just like punch it, look, they won't enter. Even if I put my whole hand in there, it is not going to enter. And well, thanks, and do it. It's a fun thing.
Okay, so this is the upside down glass of water experiment. It is an experiment about superficial tension, and we are going to see how this glass full of water it's going to retain the water with this insect gauze. We are going to use 1 glass of water, insect gauze, a piece of cardboard or a piece of a sheet of paper, and 1 recipient if the experiment fails. So first we're going to fill the glass of water. Full, yes. Then we're going to put the insect gauze. And a rubber band or something so you can hold the insect gauze. Okay. It is hard. That's it. Okay. Then we're going to use our cardboard. And oh no. Okay. There. And you can see 1, 2, 3. Oh, what is happening? This is due to superficial tension. You can see that the water is there, and you're thinking it is because it is because the insect goes, but no. Look at this. Oh no. And that is because the water received air and then it expands. Okay, thank you, and that's all.
So my experiment is the Play-Doh drifting on water one, and I'm gonna use water, a cup of water, 2 smaller containers, 1 syringe, 3 different colored markers, and Play-Doh. I'm going to start by pouring water in a glass of water, and I'll fill it around 3/4 of its capacity. I'm going to mark a line with a piece of really cute cherry blossom tape to indicate the original height of the water. Now I'll make a ball out of Play-Doh and I'll drop it into the glass. As we can see, it sinks. Now, using another piece of tape, I'm going to mark the rise of the water caused by the ball and with a syringe. I'll remove the water until it reaches its original height. I'm going to put the water that I took out of the main glass with a syringe. I'll now put it inside of one of these little containers. I'll fill the container again, up to the first mark, and put the Play-Doh in again. But this time I'm going to shape the Play-Doh into a ship instead of a ball. The goal is to make the ship float, maintaining the same mass. As you can see, I've struggled a lot. I honestly was about to lose it, until I decided to shape it more like a xiaolong bao, like a soup dumpling. And now, using the last piece of tape, I will mark the rise of the water on the container, and once again take the water out carefully using a syringe until the water reaches its original height, and I'll put the water into container number 2. As we can see, the amount of water in the 2 little containers is the same. This happens because water supports the boat by pushing bubbles on the bottom of the boat, and therefore it does not sink. The shape of a boat plays an important role in the floating, since it makes the Play-Doh a buoyant object, while the ball is dense. Even so, if I was to put weight in it, it would sink regardless of its shape, since water can only push so much.
Hi! Now for this experiment, the materials that we are going to use is a paper clip, and a glass of water, and tenemos que herramienta misteriosa. There is a fork. Come on, let's see how it works. Well, if you try this at home, you will see that the paper clip don't float if you put it in the water. But if we Gensheim put this paper here like this, I think that it's good. And then the paper clip. Oh. Now with the herramienta misteriosa, we get out. Oh, the paper clip floats. You know why? I will explain you. Well, hey again. How does this happen? This happens thanks to the surface tension that is formed by the water molecules, and this helps to hold on the water, the paper clip. Well, the paper clip is not floating really, it's only held on by the molecules thanks to the surface tension. A lot of animals have that, like the grasshoppers, the water spiders, and I think that some frogs have it too. But this is the explanation of the surface tension. Thanks.